All right. So today we have knowledge shares. So we've had a lot so far. That's great. We're going to be talking about DC-DC design and comparing converters. Um, this will be the agenda. We'll first just cover types of converters. I think it'll be a good interface, I guess, to talking about DC-DC converters and the DC-DC converter we use in the car for power supply to our entire low voltage systems. So, all converters can essentially be broken down into 4 types. And it's literally based on the input-output requirements of the converter. So I'm hoping that this section will be a good intro if you're not way too familiar into power electronics. And if you guys ever have any comments throughout the presentation, please feel free to interrupt me and yeah, ask away. Also, let me know what's happening in the chat. Cool. So back to the subject. So we have AC-DC converters, AC-AC converters, DC-DC converters, and DC-AC converters. And there's a ton of applications which we'd use for each of them. And it really requires us knowing what are inputs and outputs, like I said before. AC power is sinusoidal, it's oscillating, it has a certain phase and frequency. And so as you can see on the chart on the right, when we have it inputted, or actually when we output it, we can control both the voltage and the frequency. So these converters control both those characteristics. So anything X-AC. And then we see that when we have a converter that's outputting DC power, it's really what we're looking for, what we want to achieve is a steady reference and output current that does not oscillate and is basically a constant function with respect to time, as you can see here. So when we're talking about AC power, we really are looking at, as I mentioned before, the phase, the amplitude, and the frequency. Those are 3 main components. And depending on the phase and the frequency, and actually really all those characteristics, our design will really change. So the same kind of goes for DC, except we don't care about the frequency and phase because they don't really exist, and we just care about the amplitude of the voltage. So we're going to go into a bit about how each of these converters are designed, some of their common applications, and maybe hopefully walk through the logic just to give you guys some insight into what the design is looking like for each of these converters. So AC-DC, let's start there. So AC-DC converters, any power supply unit, PSU, it requires AC-DC converter because if you ever have a appliance that requires on power from the outlet, what you see from your outlets in your homes, in North America at least, is a 120 volts AC 60 hertz sine wave. And so that's a AC signal, but when we're dealing with any kind of components or circuits in most supplies that use anything that really uses digital logic or a controller of any sort, we need a DC supply or a power source. So we need AC-DC converters in basically any wall-powered device. And so the way that AC-DC converters usually work, and most of them really do work on this property, is the property of rectification. That word, it really means to straighten out, I guess, in quotations, an AC sine wave or AC waveform. And so the way that rectification really works, and of course, power electronics, it's a huge topic, and there's a lot to learn, especially through the internet. There's so many great resources, but I'll just cover kind of the basics of rectification, especially with the usage of diodes or thyristors. Okay, so if you learned from any class before, diodes are a PN junction, which is different doping. in the semiconductor device. So they have the properties of forward bias and reverse bias, and only conducting in forward bias. So by bias, forward bias basically means that the voltage from the anode to the cathode is, well, the voltage reference at the cathode is greater than the voltage reference at the anode by a certain amount that would result in the forward bias having a conduction, which means a current going through the diode and to the rest of the circuit. The same goes with, or actually not the same goes, okay, so diodes in reverse bias are when you have a voltage reference that's higher at the cathode than the anode, and in which case diodes, as you can see in the chart on the, actually annotation, let me take that out. Pointer, there we go. Okay, as you can see on the chart on the right, has a breakdown voltage in reverse bias that if it's surpassed, you basically destroy the diode, but up into that point, there is no conduction there is no actual conduction across the diode. So it kind of blocks out things that are like current that's going the wrong way. And with that property, we bring ourselves to the diode rectification, which basically, if you look at this image on the left, we have the sine wave. So the supply is giving us a positive current. So if this is IF, let's pretend the direction positive is this way, right? So everything let's pretend this is a positive voltage reference, right? So anything going towards, anything on the positive side of the sine of this waveform will make our diode conduct because we have a difference in potential from anode to cathode. And so we will see on the rectified wave that we have the entirety of the input, the positive sine wave. But then once we get to the negative portion of this waveform, we see that the polarity is now, like, not the polarity, but the bias is now reversed. And since the diode doesn't conduct in reverse bias, we don't see the output on the load having the negative waveform. And so with that property, it's like, this is like the basic property of how rectification works. So if we look at the top right diagram, this is a full bridge rectifier. And essentially what we see is that when you have a sinusoidal waveform going into this node, it will conduct over D1 and D3, and then using a smoothing capacitor, which is just like a capacitor, as we've talked before, is a temporary energy storage device. So it like will provide our circuit with energy when the conduction is not occurring from the source. So with the addition of the capacitor and the fact that we're like chopping off the negative sine waves of our input source, we see that we get a resulting ripple. And you'll hear this word ripple a lot in anything that has a DC conversion, that it resembles or is almost resembling a DC voltage reference. It's very close to having no oscillation, like there's a small magnitude, but it's resembling what we really want. And it's because of the properties of the diode breaking up the sinusoidal waveform in the circuit. So that is essentially the main property of rectification through the AC-DC conversions. So a typical circuit for this type of converter is that you would have a step-down transformer. So you essentially have your AC source, maybe this is from your outlet, and then you have a step-down transformer just to make it allowable operating range for the circuitry in your rectifier, not too intense. And then the rectifier circuit, as we saw on the last slide, kind of kicks in where you use diodes or thyristors. Thyristors you might not be familiar with, but they're also a semiconductor device. They have, instead of having like a P and N junction, they have they have a P, N, P, N junction. So there's like 4 total. And they operate slightly different from diodes, but they have the same like properties of the conduction in forward bias, or being forward bias versus reverse. So we get to the rectifier circuit that kind of like takes out the negative oscillation of our power source, and then to make it smoother, we have our filter circuits. And these filter circuits are giving us like both caps and inductors are temporary energy storage devices. So they really smoothen out that curve, because when we are decreasing in amplitude from our oscillating signal, they have been charging, and then they kind of let out their energy back into the circuit. So we get that ripple we saw on the last page, which is, this is what we're aiming for. And then, of course, we have the electrical load. So the only difference is that more sophisticated AC-DC converters will also have a control block for controlled rectifiers. And so if we're getting it like a AC-DC converter from a PSU, for any unit we're kind of like, or like appliance we're using, there's most likely a control block to make sure the output is stable and is not changing based on a change in input. So cool. That's like kind of a really high level how AC-DC conversion works. So let's talk about AC-AC conversion. Honestly, I couldn't find way too many common applications. Controlling power to heaters is one of them. But the essential purpose of AC-AC converters is to either vary the output frequency or magnitude, while like mostly maintaining the phase. So here, this is a diagram of an AC-AC converter, and you can see the input is like modeled by 3 phases. The output is also modeled by 3 phases, but the difference being, the chat. Okay. Yeah, but the difference being that the output, we can vary the RMS voltage or vary the frequency of the output. So they can really be like frequency or voltage controlled on the output side. And they're usually based off of thyristor logic. So last page, we talked a bit about thyristors, but here's kind of the IV curve. You can see it's a little like more like funky compared to the diode curve. It's just slightly different properties, but you could still see the reverse of the breakdown region is kind of the same properties. And this is a diagram of a thyristor, by the way. Cool. So AC-AC converters, we don't use them in our vehicle. I don't think we really use AC-DC converters in our, actually, technically we use an AC-DC converter in the charger of our car, because of course we're charging from a wall outlet. But AC-AC converters, I don't think there is a use case in our car specifically. And then we have DC-AC converters, and they're also called inverters, and very common applications are motor inverters. And they work on the property of really like bridge switching logic. And so our motor inverters are obviously, we buy them off the shelf, we don't design them, but they use a similar property, as you can see, to the full bridge inverter. So I have a pretty good YouTube video if you guys want to check out. I thought it was really clear on how the pulsing works for half bridge and full bridge, but I will try to explain it anyways. So basically, your DC-AC conversion, you're getting an input DC supply, and you want to output an AC waveform. So the way it works, okay, sorry. is that, let's just talk about a half bridge converter for now. So when you have your voltage source, a battery, which is a DC, you are basically trying to apply a clock pulse to these MOSFETs. And when you do, when they're, they have to be inverted logic, by the way, like this one will turn on when this one is not on, and vice versa. So then when you turn this guy on, you get a current loop that goes around MOSFET 1, as you can see here, period of the clock. And then when you turn MOSFET 2 on, MOSFET 1 is off, and it's the same thing. And so you can see from this diagram, the half bridge inverter, MOSFET 1, MOSFET 2 are turned on during these clock pulses. And so what you're getting is supplying your load with a source of power for kind of like a certain duration. So at the end of the day, you're getting something that looks like that is like pulsing in terms of giving you voltage to your load. So when we look at a full bridge inverter, by the way, the difference being that your load will get half the power at any point from your supply. Like, for example, this is 50 volts DC each. Well, like let's pretend this is 1 unit, you get 100 volts DC going to the load at any time. So the amplitude of the oscillation of the output is half. So for a half bridge inverter, but for a full bridge inverter, we always turn on MOSFET 1 and MOSFET 2, basically diagonal effects at the same time. So when we see the current loop, we see that we get, like, for example, for the first period, MOSFET 1 and 2 are on. The current from our supply goes through our MOSFET 1, through the load, and through MOSFET 2 back to the source to complete the loop. And we see we're dropping our total 100 volts DC during that time period. So the same happens in reverse for MOSFET 3 and 4. And what we see again is that we are turning them on at different cycles. But that will like provide us the path for having the oscillation in terms of supplying the load. So yeah, so I would strongly suggest checking out the YouTube video. The way that they actually work is using usually comparator logic, and again, like having some sort of snubber circuit is usually useful in the middle. But yeah, this is the main properties of DC to AC conversion. And you'll actually see in the video that the way that the pulsation happens is based on a PWM. PWM stands for pulse width modulation. And so the way that it works is that you are kind of pulsing the load at certain frequencies at different time periods, so that when you kind of, so when you see the output on the load, you get like this different width of duration of a high pulse at different times. And then what you can see from that is that if you compare it to this is how like this is like a sneak peek to the video, but if you look at the comparator, which usually takes in the input of a triangular waveform and a sine waveform, and those two compared will give you the width to which you PWM your FETs, you will like soon resemble a sinusoidal waveform through the pulsation of your PWM. So I probably explained that way worse than I needed to, but yeah, definitely check out the YouTube video. It's very clear. Okay, and finally, DC-DC. These converters, as the name implies, use or have an input of a DC voltage and have an output of a DC voltage as well. So we use them extensively in our car. Any I didn't really say a common application because any really like multi-voltage level system where you're taking an input voltage and you're distributing it, you have like a power management of some sort, like you're distributing it to various components and they all require a certain reference. You'll need to have some sort of DC-DC converter. And so DC-DC converter, that's a huge topic of like specific converters, but they can really be branched out into two main types, linear converters and switch mode converters. So linear converters, they traditionally use resistive drop for a lower output voltage, or they use like a shunt of some sort. So basically, the main takeaway is that the voltage is dropped on some load for the output to be at a different reference. And I'll try to also walk through, so this guy, actually, wait, I'll hold up. Let me just briefly talk about the difference and then with switch mode converters. So switch mode converters, they use a property of a switch node, which will essentially pulse the DC input to a certain oscillation that will give us an RMS of with filtration we'll just get a small ripple, but it'll give us a subset of a voltage reference. Or it can even like switch mode converters can even be designed to boost or raise voltage. So there's two main types, there's bucks and boosts. And kind of like as the name implies, bucks will give you an output that's lower, has a lower voltage reference in the input, and boosts will raise the voltage. And something that linear regulators cannot do is raise the voltage because as we have discussed, it's just a resistive or some sort of voltage drop to get to a different reference. So I'm gonna, to the best of my ability, try to walk through how each of these common types of regulators work. So we have linear regulators. One really common type is a shunt regulator. And the way that it works is the property of Zener diodes. So how Zener diodes work is that they conduct, like our diodes we were talking about back in slide 1, they don't conduct in reverse bias, but Zener diodes, they do. They have a specific voltage that once is surpassed on their cathode will actually allow current to conduct through the diode and kind of be shunted to ground. So these regulators really use that cool fact about Zener diodes. And so there's a resistor on the cathode of the diode, and the output voltage is also at the cathode of the diode. Input voltage is on the other terminal of the resistor. And so basically, when you have your input voltage, let's just say this is like a 9-volt Zener diode, and this is a 12-volt input voltage. So 9 volts will essentially be dropped across the Zener diode. And so we're getting 9 volts here. And then the current is being limited by this series resistance. So there's a small amount of current to maintain. Oh my God, Siri got triggered. Okay. So there's a small amount of current that goes through this diode, and the rest is kind of powering your circuit that's using this input power. So this is really how it works. It is a linear regulator because it is dropping voltage across a passive element, and then that is the way that you get a reference. And then the way that a low LDOs kind of work is based on this logic. So I'll try to walk through that again. Let's just imagine the pass device. In a circuits course, you've probably heard of voltage controlled current source. So let's imagine it as one of those. So basically, it controls current, but it controls the current by a reference of voltage. So the way that these guys work is that you have your input voltage on this side, and you have an error amplifier here. If you guys are unfamiliar with error amplifier, it's basically an op-amp that's in a feedback configuration that will allow the output to tell the difference in the voltage reference versus the, or output the difference in the voltage reference versus the voltage reference at the other terminal, at the inverting terminal. So what we get is that the output of the error amplifier will give us a specific voltage that is the error between the output node and the reference voltage. And so that will essentially control a transistor or a pass device, some sort of transistor that with the specific voltage at the base or the base of the transistor, it'll control the current that can be conducted from collector to emitter. So how that actually drops our load is that since we're controlling the voltage on the load, we can see that if the load is a specific resistance and we're not changing this resistance, it's fixed, right? We have a certain current that we control that goes across this load, and by controlling that current, we control the voltage that drops across it. And with that, the error amplifier, no matter the V input, if it changes slightly, it's basically pulling for what the voltage is, and it'll take that input and it will adjust the voltage input to our voltage controlled current source to limit the current that's being that's going into the resistor. So that's kind of how they work. And now we will talk about switching regulators. So these are I think switching regulators are pretty cool. They work a lot on the basis of having these temporary energy storage devices. So this is a buck converter and this is a boost converter. And I know I've been dragging this meeting on pretty long, but I will try to explain them both. So inductor, okay. So the way that it kind of works is that you have your DC load, right? But you're trying to, depending on what you're trying to drop out on the V output, you're trying to get an RMS value from your oscillation of like supplying the load with power. Also like smooth it out later with to just make it a ripple. But you're trying to get an RMS that will essentially be a lower value than your input. So what do? You essentially have a signal, a square wave going to your transistor. And what that does is that when the transistor is on, your voltage source is supplying current to, or is completing the path like this. So it's going through the inductor, it's going through the load, it's going through the load, and it's going back around. So you're basically charging our inductor and you're charging our capacitor, just because they're all elements that are part of the circuit when this transistor is on and connected. And so the way inductors work is that they create a magnetic field, and while you're charging it, this magnetic field is expanding. So we're still getting current going in this direction. When we turn off the transistor, so the clock or the square waveform is low, we actually have this isolated, right? So our V input is not actually providing power at this time. What is happening is this inductor is like, oh no, my current source is gone, and I, an inductor, do not like sudden changes in current. I actually can't respond to them instantaneously, as we might have talked about before with Liam's knowledge share. They work on a property of differential in current. So what the inductor will do is, as its magnetic field is collapsing around it, its polarity actually changes and it becomes a source of power. So what happens in the current is that the current goes still through the load because the inductor is providing it, and then it goes through our flyback diode. So this diode, it continues the loop as our input source is now disconnected. And then what our capacitor does is, it's like the inductor's assistant. It was charged during the on time of the transistor. So now it provides its own energy source and contributes to the load. And capacitors, unlike inductors, don't like or can't deal with don't have an instantaneous voltage change. So the capacitor helps maintain that voltage we're seeing on the output of the load. And so what happens is that while we're pulsing this, we're kind of like getting an RMS value that's a reference, that's basically a lower reference, at a lower reference. And so we are bucking the voltage on the load. So yeah, that's how it works mainly. And you'll see that again, we'll be seeing like a kind of triangular ripple on the output of this load after filtering it with capacitors and such. And then we come to the boost converter, and it's special because there's no other converter that really like gives you a higher reference on the output than the input. But the way that these guys work is that they essentially, they turn on this transistor, they charge the inductor, right? And so when this transistor, they're just charging the inductor. They aren't really doing anything else because this is like a shunt to ground when this FET is open. And so it's just like a loop here. But then when they close this transistor, this inductor is now really full of energy. It becomes the power source. But wait, so is the original power source. So if we imagine this inductor having the voltage or the potential to output the similar voltage as the input, we're basically getting double the power. And so this power then goes and goes through to the load. It's getting charged from the capacitor again to smoothen it out, and we get this kind of circle. But we see that our amplitude of our waveform is higher than the amplitude of the input voltage because of the inductor, and so we get a boost in terms of the RMS we're seeing. RMS stands for root mean squared. It's basically a DC way to measure an oscillating waveform. So hopefully that made sense, but again, there's like, if you're really interested in this topic, there's tons of resources online, but I just wanted to provide a quick intro. And so now the main thing we are concerned about as designers at a system level is which converters to use in which cases. So there are clear pros and cons to both using linear voltage regulators and switch mode converters. So the pros to linear voltage regulators are they're really clean output sources. There's no switching, there's no noise. They're highly integrated components. We can just get an LDO and we basically need no passive elements on the outputs, and they're extremely cheap. The cons are they're not efficient at all. And to tie with that, they lose power in the form of heat. So that contributes, of course, to the inefficiency. We don't want to lose power in the form of heat. And so, yeah, so the power is actually lost on that passive switch, passive device here, based on the current that it's regulating based on the error amplifier. But essentially, it's there could be too much loss depending on the drop we're expecting. So if we need like a 150 volt buck converter to like 12 volts as we use in the car, that this is not a good option. Switch mode converters, on the other hand, are highly efficient, and they can also boost voltage. The cons, of course, are that they have an output ripple and noise that's not quite DC, and so they require external components and filtration, which adds to the complexity of the solution. They're also not cheap, usually. So I will now start to talk about the actual DC-DC converter in our car and how I kind of came to design decisions. This meeting will cut out in 2.5 minutes. We will just resume the recording as well. So, okay, so I'm going to cover the input filtration, the bulk capacitance, the Vicor module we're actually using, and dealing with inrush current, which I will explain to you later, but is a product of doing multiple revisions of this board and realizing I didn't consider some things. Okay, Vicor module design guide. This is since Vicor is the manufacturer providing us with the switching inverter. They really know the key characteristics about what the switching frequency is, how that kind of works internally, and what kind of noise or ripple that we're really expecting, or what kind of transients we're expecting. So Vicor gives us this extremely detailed design guide. And so majority of the board was just reading through the design guide and deciding what we needed to keep. And so the rest of the slides, they have been validated by either design guide or the data sheet. So common mode noise. Let me start by actually looking at the DC-DC converter. So here are the schematics. I'll get to this section later in the slides, but I was thinking we could just linearly go through all the components. So we start with our common mode choke. What is common mode noise? Well, Liam explained it pretty well last week, so I just copied his diagrams. But essentially, it's different from differential noise because noise carries out on both lines, basically due to stray capacitances in the module. So ways to deal with our common mode noise that have been implemented in the DC-DC converter. Again, we don't want this noise to propagate through the lines. We want to have a steady DC source and a steady DC output. It's really that. So the common mode choke, as Liam described in our last sync, is basically a way that the wires are wound around wires around a core, and how it works is that they're wound in opposite directions, so they kind of cancel out their noise source, which I guess are these what's it called?